Hey folks, I got an example of a circuit with a capacitor and resistor. We're going to charge the capacitor up, and then when it's fully charged, we're going to discharge it. This is part of a packet. If you have the packet, great. If not, you might want to stop and copy this information down. Now, we're not learning how to do it. We've already talked about how to do it. So my goal here is to kind of show you some shortcuts, some things to think about. So the first question is, what is the time constant tau for this circuit? So that's the easy part. That just equals RC. Now R is 20 kiloohms and C is 30 microfarads. So we get a 600. Let's do some shortcuts on the powers of 10. You've got a kilo times a micro. That's 10 to the third times 10 to the negative sixth. That is 10 to the negative third. So this would be 0.6. And it is a time constant, so it is actually in seconds. If you want to know why it becomes seconds, see me before or after school, and I would be very happy to show you why a ohm times a farad becomes a second, but it does. All right, number two, find the charge as a function of time. So the first thing I'm going to do is I'm going to find the maximum charge. So that's just going to be C times E, which is 30 times 10, which is 300. Now it's micro times nothing, so it's microcoulombs. Now we're going to use the equation Q as a function of time equals that Q max, 300. Now, do you want the e to the negative t over tau, or do you want the 1 minus e to the negative t over tau? Well, we want the function that starts at 0 and ends at 1, and that is your 1 minus. So it's 1 minus e to the negative t, and the tau is 0.6. So that is your charge, and it's microcoulombs. So that is your charge as a function of time. The Q at 0 seconds is 0. The Q after a long time is 300 microcoulombs. Number three, ask you for the current as a function of time. When you first close the switch, the capacitor is going to behave like a wire. It'll be as if charge goes right through it. So what you have for your current, your maximum current, is just going to be V over R, which is 10 over 20 kilo. So this would be 0.5 times 10 to the negative third. So you could say half of a milliamp, but what would be more appropriate is to say 500 microamps. Okay, so that's your maximum current. When you first close the switch, your current will be 500 microamps. But then as time goes by, the capacitor will charge up and the current will die. So for the current as a function of time, we want that 500. And then do we want the e or the 1 minus e? Well, we want the function that goes from 1 to 0, and that is e to the negative t over tau, which is 0.6. Okay, so that's your current as a function of time. Number four, how many time constants until the capacitor is 90% charged? Okay, so we're looking at this equation, and I'm just going to write it this way. Q as a function of time equals Q max, and then 1 minus e to the negative t over tau. So we want to know how many taus is t. We're going to solve for t. They want the charge to be 90%, okay, of the max value. So they want this to be 90% of that. So that's the shortcut way of doing this. And then 1 minus e to the negative t over tau. So then you get negative 0.1 equals negative e to the negative t over tau. And then you get the time. So then you take a natural log of, all the negatives drop out. Take a natural log of both sides. So natural log of 0.1 equals negative t over tau. And if you solve for tau, if you solve for t, you get negative natural log of 0.1 times tau. And if you plug negative natural log of 0.1 into your calculator, you get 2.3 time constants. So the time it takes to charge the capacitor 90% is 2.3 time constants, which would be 2.3 times 0.6. So that time in seconds would be, if you take 2.3 times 0.6, I get 1.38 seconds. So that's how many time constants go by and how much time goes by before when the capacitor is 90% charged. All right, number 5, total charge delivered by the battery. Okay, so the total charge delivered by the battery. Oh, sorry, is that total charge delivered by the battery? Let's see. Number 5, total energy delivered by the battery. So the work done by the battery is going to be the total charge times the voltage of the battery. Okay. The charge that we figured this out in number 2, that is 300. So it's 300. Now that's a micro, right? And then E is 10. So this would be 3,000 micro or 3 millijoules. Okay. The other part of this is that it says what's the energy stored in the capacitor. So the potential energy of a capacitor is 1/2 QV. Now when the capacitor is fully charged, the Q is 300 micro and the V is 10, and you would get 1.5 millijoules. You're going to get half the answer you got in the first part of this. So the last question asks how much energy is dissipated by the resistor. Well, the work done by the resistor will be, well, if you started with 3 millijoules, but only 1.5 of them got to the capacitor, then that means you're losing 1.5 in the resistor, and that's turning into heat. Okay. All right, question 6. How much energy delivered by the battery in the first half second? Okay. So for number 6, how much energy the work done by the battery will be Q times E, okay? But we got to figure out Q. So Q after half a second. So Q is going to be 300 times 1 minus E to the negative 0.5 over 0.6. And if you plug all that in your calculator, you're going to get 169.6 microcoulombs. That's Q. And then you multiply that by 10, and that'll get you the work. So the work would be 1.696 millijoules. All right, the 7th question asks, how much energy delivered to the capacitor in the first half second? Okay, so that's not going to be half of that. So we have to use one of our equations. So work equals 1/2 QV. So we could use that, but we don't know what the voltage is of the capacitor at this moment. So knowing that Q equals CV, you can get work or energy stored in the capacitor is Q squared over 2C. Now that I do know. We figured out Q, right? It's this right there, okay? So we have 169.6. Now that's a micro, so that's 10 to the negative 6th squared over 2, and the capacitance is 30 times 10 to the negative 6th. So your 10 to the negative 6 cancel, but you have one left over up there. So you get, I get 479 microjoules, which is 0.479 millijoules. And I'm going to write all the energies in millijoules so that I have my answer in millijoules. So the work done by the battery was this. The energy stored in the capacitor is only that. Where'd the rest go? Well, it went into the resistor. So the work done by the resistor is going to be the energy stored in the capacitor minus the work done by the battery, and you get negative 1.217 millijoules. So the resistor dissipates that much energy as heat. Okay. All right. Then, so that's number 8. Then once this capacitor is fully charged at 300 microcoulombs, they open the switch, they remove the battery, and then boom, they close the switch. Okay, so I'll switch colors because now we're going to be discharging. Okay, so if we're discharging, they want Q as a function of time. Okay, so for this, Well, that'll be the max, which is 300. Okay, and then now you want E, because you want to go from a max to 0. So it's e to the negative t over 0.6, and that would be microcoulombs. Okay, so that's number 9. Number 10, what's the current as a function of time? So the I max, before it was 500, it's going to be that again in this case. But it's going to be negative because the current's going to go the other way. We talked about that in the last video. And you're going to have your e to the negative t over 0.6. And that would be milliamps. Okay, or no, sorry, microamps. Okay. Then number 11 says how many time constants for the capacitor to be half discharged. So I'm going to use equation 9, but I'm going to call this Q, and I'm going to call the 300 Q max, and then e to the negative t, and I'm going to leave the 0.6. We're going to call that tau. So we want to find how many time constants that is. So we want the charge to be half of the total. So you just do it that way. This is half of that. E to the negative t over tau, and now you're solving for t in terms of tau. So you do natural log of 0.5 on both sides, so you get natural log of 0.5 equals negative t over tau, and so t would equal the negative natural log of 0.5 times tau, and this t should not be cursive there. If you plug those in, you get 0.693 time constants. And your time constant is 0.6 seconds. So if you were to plug that in, I get 0.416 seconds of actual time. All right, and the last one is, what is the charge when the current is 200 microamps? Okay, so we're going to use the result from number 10. I want to make this 200. That has to equal 500. Now I'm looking at only the magnitude, so I'm leaving the negative off. E to the negative t over 0.6. Now a little shortcut here. We're just going to solve. We could solve for time. We got to figure out when is the current. At what time is the current 200 microamps? We need to know time, but we're going to shortcut here. We're going to solve for this. So this is just equal to 2/5, right? Okay. And then we're going to plug that into, we want to know the charge at when e to the negative 2 over tau equals that. So now I'm going to use, and I'll change colors just for the fun of it. We're going to use our Q equation, and Q is equal to 300. So I'm using this equation from number 9 there. But I know what e to the negative t over tau is. It's 2/5. So our answer is 2/5 of 300 is 120, and that's microcoulombs. Now you could solve for time and then plug it in your calculator, but try to make some shortcuts. So I went through that kind of fast because they're all really straightforward problems if you know the equations. Again, use your common sense and think about your units. Use shortcuts on the powers of 10 and such. It helps so much. All right, I hope that video was helpful, and thank you very much.